Good morning, Abyssers. Welcome to Calculus. Okay, we can stop the music. Alrighty, we're talking about error. And when I started last time, I was talking about something called a Taylor polynomial error.
Are there notes that I can get?
Yep. Okay, it will be 9-7. I'll go back to them. Okay? I think you have them already.
Yeah.
Okay? But I'm restarting, okay, because I did such a poor job on Monday. Okay? And the Abyssers out there know it. They could tell. And it's also called the Lagrange error.
What are you doing right now?
Okay?
It's just a problem that it's...
Yep, I'm just going to go through and explain it. All right? So you have a polynomial. And the polynomial is defined like this. F of c plus f prime of c times x minus c, and then plus f double prime of c divided by 2 factorial, x minus c squared plus dot, 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 right? And you have this function. And you're going to plug a value in here. Oh, let's call it b. Okay? And it's approximately going to be f of b. And so, because you're not going to go, this goes on to infinity, because you're going to use a finite number of terms, there's going to be an error. There's going to be a difference between the two, between this and the actual number. That actual number, which is called a Lagrange error, is computed this way. And I'm going to use this letter first, m. And it's n plus 1, which means it's based on the next term, the next derivative. X minus c to the n plus 1. So you can see that that's generated from this polynomial. And this m, the reason they choose the letter m, it's going to be the maximum value from the derivative, and this means derivative, the n plus 1 derivative. The maximum value you can get from that derivative. Now sometimes, a lot of times, you're going to find that value is going to be between, and we're going to call it z, and it's going to come from a closed interval between x and c. So that's why you see this sometimes. But what you need to focus on, it's the maximum value that you can get from that derivative. It can come from some number in this interval, this closed interval, and we'll look at both examples. One in which it is within that interval, and one which it is not. Okay? So the example I'm going to use to begin with is I'm going to use the cosine of x to be my value, my function, f of x. And c is going to be 0, so it's going to be a Maclaurin series. And I'm going to have n equal 3. So I'm going to come up with a third degree Taylor polynomial. That's going to be centered around 0. So the first thing I'm going to figure out is f of 0. And what would that be? 1. So I'm going to take the derivative and plug in 0. The derivative of cosine is? Negative sign. So I got the negative sign of 0. And that's going to be 0. Correct? I'm going to take the second derivative. So the derivative of a negative sign is negative cosine. And I'm going to plug 0 into that. And that's going to give me what? Negative 1. And I'm going to come up with my third derivative. Plug in 0. Derivative of negative cosine is? Sine. I'm going to plug in 0, and I'm going to get 0. Correct? So if I follow this, I'm going to have 1. This will be 0. So I'll go to this term, which is a negative 1 over 2 factorial times x minus 0, which is x, and then that's going to be squared. Correct? Right? Would everybody agree with that? And then if I go to the third one, it's going to be 0. So my third degree polynomial is going to be 1 minus 1/2 x squared.
Why is the
Are we okay with that?
Yep.
Okay. And I'm going to, it's going to have some error. And what I'm going to do is I'm going to use it to estimate. I'm going to let x equal pi over 3.
Why did you choose pi over 3?
I just arbitrarily picked one. Okay? You want to know the reason, real reason I picked it? Because I know the cosine of pi over 3 is 0.5. It's an easy one. It's a nice, easy decimal. As opposed to the square root of 3 over 2, which not everyone may know that's 0.866. So, but that one they know is 0.5. All right? That's the reason why. All right. So when I plug it in here, there's going to be some error, correct? Because I only went so many terms. Well, what I'm going to do is I'm going to figure out how close I am. I'm going to figure out the Lagrange error. I'm going to use this idea. Okay? So notice that I went up to n equals 3, so I'm going to have some m over 4 factorial. And I'm going to multiply that by pi over 3 minus 0 raised to the 4th power. Okay, my closed interval is going to be from 0 less than or equal to z less than or equal to pi over 3. So here's c, here's x. And m is the maximum of the 4th derivative. So if I come over here and figure out the 4th derivative, what will I get?
How do you know m is after 4?
Because it's one more than my degree of polynomial.
Is that all that m is?
Yep. It's the derivative of it. So if p of 3 would be 7, then I would have the 8th derivative. Okay? It's the maximum that derivative can be. Okay? So what's the 4th derivative here? Is it cosine? Okay. What's the maximum that could be? 1, correct? Because sine and cosine oscillate between 1 and a negative 1. So the biggest it could be is 1. Now notice 1 is not in this interval, is it? Maybe it is. Pi divided by 3 is greater than 1, isn't it? So 1 is in that interval, isn't it? Right? Yeah. So I'm going to put 1 because that's the maximum value. And I'm going to have 1 over 4 factorial times pi over 3 to the 4th power. And I'm going to figure that out on my calculator. So I'm going to, on my calculator, I'll bring it right here. Can you see that okay? I'm going to take pi divided by 3. I'm going to raise that to the 4th power. I'm going to divide that by 4 factorial. What is 4 factorial? 24. So my error is 0.0501. This right here is my Lagrange. Okay, maybe it's got a G at the end, not a D. My Lagrange error.
So that's just how far away your estimate is from the real answer?
Correct. That's how far away. Now, sometimes you can actually figure out the exact error it is, okay, which we can in this case. All right, sometimes you can. But usually that is never greater than this. All right, usually the actual error is less than the Lagrange error. So this is what's called a worst case scenario, which, that's not too bad, is it? Now I'm going to figure out the actual error because I know what the cosine of pi over 3 is. It's equal to 0.5. That's the actual number. If I put pi over 3 into my equation, which is 1 minus 1/2 times pi over 3 squared, right? That's my equation I came up. And I computed that, and I'll do that right here. 1 minus 0.5 parentheses. Oops. Where's the delete button on this thing? I get this. This computed to be 0.4517. So I have some error between that, correct? The real error is 0.5 minus this. Which is approximately 0.048. And I said my Lagrange error was going to be 0.05. Well, I'm pretty close, aren't I? Now, the more terms I go, the less error I have. Does that make sense? Okay? All right, so let's go back to this. Yep.
Why did you take down all the posters in here?
Pardon?
Why did you take down all the posters?
Because we had MCA testing yesterday, and I gave it to 10th graders, and it was the reading test, and the state of Minnesota believes that those posters would influence those students who were taking the test. So the Schroeder equation, the Pythagorean theorem, the definition of a derivative, all will lead to inaccurate testing. So is the life of being an educator. Sometimes the truth is not important. All right, we ready for this one? Okay? So my function is sine.
We already did that.
Did we finish it?
Yeah.
Okay. So I can
I don't
go.
really know, actually.
Can I do it again in this fashion?
I mean, on a space.
I don't have the room, but I guess you can, yes.
Okay.
I would like to see
Alrighty. So I'm going to write this down. F equals sine. F prime is equal to cosine. F double prime is equal to negative sine, I believe. F triple prime is equal to negative cosine. And I have to go to the fourth to get to sine. Does that look correct? Is that what I did yesterday? Okay. So I'm going to have, what's the maximum value can this be? 1 over 4 factorial. And I'm going to have x minus c. So x is equal to 0.1 and c is equal to 0. So I have 0.1 raised to the 4th power.
Why is c equal to 1? It's just c is equal to 0. It means 0, yeah. Why? Because it's a Maclaurin.
Because it's a Maclaurin polynomial.
So that
If it was a Kruger polynomial, c would be 3. But Maclaurin c is equal to 0. Is that true every single time? Yes.
Okay.
So they'll tell you Maclaurin and then they won't. Every other time they'll tell you what c is. But when it's Maclaurin, it is automatically 0. Okay? And so did I figure that out on the calculator? Was it like 0.000004 or something like that? Was it like 5 zeros?
Yeah.
4. And so what I'm saying is this, that when I actually figure out the sine of 0.1, and I put 0.1 into my third degree polynomial, it will not have an error of more than that. That's pretty good considering how easy this function is. So if I actually figured it out and I would have 0.1 minus 0.1 to the third power divided by 3 factorial, it's going to be at least within that, maybe even closer. That's what it allows me to say. I think that's more understandable than what I was trying to do before. Yeah, isn't it a lot easier?
Looking at what you did
I have no idea.
Don't even know what
Oh yeah, what I did on Monday was icky.
Oh, yeah.
I don't disagree with that. Okay? That's why I woke up and I said there's got to be a better way to explain that.
So is the Taylor polynomial?
It's a third degree Taylor polynomial. It's generated from these, right? I didn't go through it this time. And you'll know that when we put 0 in here, we'll get 0 here, correct? 1 here, negative 1 here, and that's why you see those numbers there.
Okay.
Does that help?
Yeah.
And what's nice about Maclaurin is you have x minus 0, so the x minus c just becomes x squared or x cubed or x to the 4th or whatever.
So when it says use Taylor's theorem to approximate, that's just when you do the m over n plus 1.
Right, what we're going to do is we're going to look at the upper bound. I'm going to talk about how you get that. Okay? And I'm going to compare it to the exact value. All right? So this is E, right? Okay, so what's f of x? What's f? Do you suppose? This is my Taylor polynomial. This is p of 5. Would you agree with that? How do I know it's p of 5? Because I got 5 factorial here. I got 1 to the 5th, correct?
Why would that be p of 5 and just...
Because I got 5 factorial and I got 1 to the 5th.
Yeah,
And this is 0, 1, 2, 3, 4, 5.
Yep, I didn't get the 0 part.
Okay. So what do you think f is?
X to the 0.
Well, x, e, well, how do I get 1 here?
X to the 0.
How about e to the x?
Yeah, that's what I said.
And when I plug in 0, don't I get 1? Okay? And when I take the derivative of e to the x, what do I get? E to the x.
Oh, I
And when I take the derivative of that, what do I get? E to the x, don't I? And if I plug in 0, aren't I going to get 1 every single time?
Couldn't you still do like x to the 0? Because it's going to be 1 every single time. Like,
Yeah.
how do you.
X to the 0? Because I'm estimating e. And e is to the first.
I see.
Is that, are you okay with that?
Is it going to tell you if. Yeah.
So
Yeah,
C
how do you
0.
know if it's asking for e?
The C is 0.
Well, if I would have had sine to the first, I'd have something different here.
Is
Correct?
it going to tell you like sine to the whatever? Or.
Yeah. Yep. It'll tell you what you're trying to approximate.
Okay.
Right?
Yeah.
Okay? So e to the first is approximately that.
Is that E to the 5th?
No. Because I'm putting 1 in here all the time, right?
You're right, you're right.
Correct?
Putting 0?
And what I'm going to have is
Yeah, I wanna put
c
0.
is equal to 0,
Oh.
and x is equal to 1, and 1 minus 0 squared is 1. 1 minus 0 cubed is 1.
Why is x equal to 1?
Because that is the only way I can get 1. Because e to the first, I'm approximating e to the first,
Shouldn't
right?
it be 0?
I'm approximately e to the first, correct? Right?
Yeah.
Right?
Yes.
I don't.
Right.
So this is my e to the x is the same as 1, because that's f of 0, plus 1 times x plus 1 times x squared over 2 factorial plus 1 times x cubed over 3 factorial plus 1 times x to the 4th over 4 factorial plus 1 times x to the 5th over 5 factorial. Wouldn't you agree that's what e to the x is? Because the derivative of e to the x is e to the x, and when I plug 0 in here, I get the derivative right here of 1 every single time. Right? That's my polynomial. And then if I wanted x e squared, well, then I would put a 2 here, a 2 here, a 2 here, a 2 here, and a 2 here. If I wanted e cubed, I would put a 3 here, a 3 here, a 3 here, a 3 here, and a 3 here. But if I look up here, they're all 1s, aren't they? So what was substituted in there? 1. Does that make sense now?
They're confused because you're plugging 0 into f to get the 1 on like the left side of your paper,
Yeah, this right here gives you the derivative.
but you're plugging 1 into the actual function, so that it's
Right, if I center this function around 0, I get this equation. Would you agree? If I center it around 0.
Question.
Yeah.
And if they want us to do e squared, would they have given us the e squared in the beginning part?
Exactly.
Oh, okay.
But it still has, it'd be centered around, that's what I'm saying. If I would have had e squared here, the difference is I would have had a 2 here, a 4 here, an 8 here, a 16 here, and a 32 here.
Okay, that's making sense.
Okay? If I would have had e to the 5th, I would have a 5 here, a 25 here, a 125, 625, 31,100, or 3,125 here. Okay?
So you're putting 1 in for x because.
I'm estimating the value of e to the 1st by putting 1 into this Taylor, this 5th degree Taylor polynomial.
So that's like in the last one how x equals 0.1 because it's sine of 0.1.
Correct. Exactly. Yeah. So right over here, I would say sine of 0.1 is equal to 0.1 minus 0.1 cubed over 3 factorial. And over here, I've got e to the first is equal to that. Okay, thank you. I think that helped out a lot. So I'm going to figure out the error. Okay, so do you see where I have a closed interval? X is equal to 1, c is equal to 0. So my closed interval is from 0 to 1. Correct? Right? Okay, now, so I'm going to have m, and I've got to go to the sixth derivative. Well, sixth derivative is going to be e to the x, correct?
Yep.
Right?
Yeah.
And I'm going to have 6 factorial here. I'm going to have 1 minus 0, x minus c, raised to the 6th power here, correct?
Yep.
And now I got to figure out the maximum value of this derivative, correct? Now, unlike sine and unlike cosine, it doesn't oscillate. It keeps getting bigger forever, right? Because this graph looks like this. But I'm just looking at an interval from here where it's 0, from here to where it's 1. Correct?
So its max is e.
Its max is e. Exactly correct. Awesome. That's what it is. E is my max.
Good job.
So this is going to be e over 6 factorial. That's my error.
Wait, so what's the m?
M is e.
M is your maximum.
M is the maximum this derivative can be on that interval,
So if it was like ln x, it would be.
which is what we're going to do.
Okay.
Okay? Yeah,
That's the worst case scenario error.
that's the worst case scenario.
So that's the difference between the actual value and what?
Right, the difference between the actual value is e, correct?
Yeah.
Right?
So
And the difference between that and, okay, 2 plus a half plus 1/6 plus 1/24 plus 120th is my actual difference.
okay.
This is the actual error,
And the other one's the
Lagrange error. Because I know what e to the first is. It's e, right?
So then why wouldn't we just use the actual error?
Yeah.
Because you know it this time. But we didn't know what it was with sine of 0.1, right? Okay, that's like on the other one, when I said, okay, what's the actual error of the cosine of pi over 3? I know what that value is, point. But there are functions in which I don't know what the error is, okay? In fact, I get data, okay, collected from a real-life experiment, and I have a function that models that data. Well, then I got to figure out, all right, I have this data. What's my error if it converges to a particular value? You understand what I'm saying? And this is a method that I can use. Does that make sense? All right. All right, so let's look at this. Here's the natural log. So we don't know n. I want my error less than this. I know my c equals 1. What's my x equal to? 1.2. Perfect. Okay. What's my f of x equal to? ln of x. So that means f of 1, right? Because I put c in there all the time, right? That's what goes in there. What's that going to be? What's the ln of 1? E to what power is 1? What's the derivative of the natural log? What's the second derivative? What's the third derivative? What's the fourth derivative? Okay? Dot, dot, dot. What's f to the nth derivative? Well, what's happening here? Positive, negative, positive, negative. I got a negative 1, right? It's alternating. To what power? N plus 1? Yeah, because when it was the first, it was positive, correct? When it was the second, it was negative. Over here, x to what power? N, perfect. What's this? It started out as 1, then went to 2, then went to negative. Started at negative 1, then went to 2. What?
N factorial minus, or n minus 1 factorial?
N minus 1 factorial. Because this is 3 factorial, isn't it? Right? Okay. Does everybody see that? So then what is, remember, I need to know what the derivative of the n plus 1 is, correct? Right? To know my m. So this is going to be negative this to n plus 2. This is going to be x to the n plus 1. And what is this going to be right here for factorial?
N.
What?
N.
N. So, I know I want my error to be less than 0.001. Down here I have n plus 1 factorial. Here I have an m. What's that? That's the maximum that my n plus 1 derivative can be. And over here I'm going to have 1 minus 2 minus 1 to the n plus 1 power, correct?
Is that just like you didn't leave enough space? Or like what? Yeah, why? So like,
Is it up above?
is that multiplying it by the?
It should be this. If we're 1, if you want. Okay, where the 0.2 came from?
Yeah.
Okay. So, my z is between correct? Okay? So, let's say I would go to this derivative, and I had to decide in this interval, right? Because the natural log keeps growing, correct? It keeps getting bigger, like e to the x keeps getting bigger, correct? Which would give me a bigger value if I plugged in here? 1 or 1.2? 1 would be, correct? What about it? Remember, this is an absolute value, okay? So that's the thing you got to remember. What about here? 1 or 1.2? 1, correct? Because when you divide by a bigger number, it gets smaller, doesn't it? So what do I want m to be? 1. Okay, so I'm going to have 1.
Is Z M?
Is Z m? Oh no, it's Z, excuse me. Z is the value I'm going to pick to put into here. So if I put 1 into here, okay, I'm going to put 1 into this derivative, okay, I'm going to get m is going to be, remember it's absolute value, so it's going to be n factorial over 1 to the n plus 1 power.
Where does Z go into that?
Z is going to, what?
Where does Z?
Z is some number between 1 and 1.2, closed interval.
Okay.
So if I put 1 into these derivatives, right, the absolute value, I maximize them, don't I? If I pick any number bigger than 1, it makes these derivatives smaller. So the maximum value I want to put within this interval into these derivatives is 1. And if I do that, I get this value as my derivative. That's what m is. Okay, just like when we had e to the x, we put 1 in there, and Olivia said, e's got to be my maximum value, correct? Because my derivative was e to the x, so 1 was the biggest number I could put in there. Okay, so I'm going to put 1 into this derivative. So I'm going to have n factorial over n plus 1 factorial times 0.2 to the n plus 1.
Where'd the n plus 1 factorial come from?
From here.
Where's the 1?
Yeah, where's the one?
I put the 1 in here. And that x equals, or z equals 1.
What in Nard? Okay, so like, it would have been z to the n power if it wasn't 1, or what?
All right.
Can you do it with
For-
1.2 just to show us where you're putting it?
Yeah, okay, if I put 1.2 in here, which is better? F of, which is better? 2 to the 1.2 cubed or 2 over 1 cubed? Which is bigger?
I mean, we get why you're doing that, but I don't get where the 1 is going. in
For
this.
x. One's going in for x.
One's going in for x right here.
With the m and the z and the x's.
Okay.
in the end.
Okay, m, okay, let me back up. I understand where you're confused. M is equal to the fourth, the n plus 1 derivative with z put into it. Z comes from this interval. And I choose a z that makes this the maximum.
Right, but then you put the maximum of, or the absolute value of m was n factorial over 1 raised to the n plus 1 or whatever on the bottom.
Right? That's what that is.
X to the m plus 1.
Right.
Oh.
So then once you put it back into m on the left side, like you just went back to putting the n plus 1 factorial on the bottom. Like where'd the other bottom go?
Yeah, where did the 1
That's what I'm
to the n
confused about.
plus 1 go?
Because the 1 to anything is this one.
Well, I'm putting 1 in here,
Oh.
correct?
Maybe 1
Right? I'm putting 1 into here.
1 to n number.
Because it has to be positive. So if it's negative,
But 1's not n, 1 is x.
Correct.
Any number
so
equal
1 to
n.
infinity.
What is this?
Start. What? Okay, we're good.
Still
Never
1.
mind. Keep going.
Okay.
What?
Okay.
Right?
Wait.
Ryan, there's nothing to wait for.
So m
Oh no, got it.
is equal to n factorial.
Power is 1. I'm like,
Right.
Okay?
Yes. On the same page now.
Are we okay here? Now or not?
Yes, we are okay there.
Okay. And that has to be left to 0.001, correct?
yep.
So what does this simplify to?
And 1 over n plus 1.
0.2 to the n plus 1 over n plus 1, correct? And I want to put numbers in there.
Yeah.
Okay.
Okay.
Are we okay with that? Okay, so now you're going to get your calculators out. Here's n. Here's 0.2 to the n plus 1 divided by n plus 1. So if I put a 1 in there, take 0.2, square it,
Everything is so messy.
and divide it by 2. What is 0.2 squared divided by 2? I get 0.02. Is that right?
Yeah.
Okay. Now you're going to take 0.2 and cube it and divide it by 3. What do you get? Point what? 0, 0.002? 0.008 divided by 3, am I right? Take 0.2 cubed divided by 3. Don't you get 0.002 something?
2, 6 repeating.
Okay, so now put in 3. So take 0.2, raise it to the 4th power, and divide it by 4. You got to get a number that's smaller than 1,000th now. 0.000 what?
4.
4. Okay, so I've got to go 3 terms. I've got to go there.
That's the degree of the Taylor polynomial.
That's the degree of the Taylor polynomial. I only got to go to a degree of 3 to be that accurate. And that's the higher end. Okay? All right, so let's try this one. What's C? 0. What's X?
0.1.
So I have this. M over n plus 1 factorial times 0.1 minus 0 n to the n plus 1 power, and I want it less than 0.001. I have cosine. What do I know about the f plus 1 derivative of cosine?
It's oscillating.
It's not going to be any bigger than what? Ever.
1.
1. Ever. Correct? So I'm going to put in the worst case. It can't be any bigger than that.
Is that 0.1?
Yes.
Yeah, because 0.1 minus 0 is 0.1.
Oh, okay, yep.
So I'm going to plug in some numbers.
Is this the only way to do it? Is like trial and error?
On this case, yeah. When you have factorial, that's the problem. Okay? So when I put 1 in there, I'm going to have 0.01 squared divided by 2 factorial. So 0.01 divided by 2 is what? 0.0 something. 0.005? 0.005? I think I'm right. If I do it in my head.
Yeah.
I'm pretty close. So my guess is this, 0.1 cubed divided by 6, which is 3 factorial, is a lot smaller than 0.005. Am I right?
1, 6,
How many zeros?
3, and then you get a 1.
And then I got a 1? Well, that's all I need, right? Because that's less than this. So I just got to go I just got to go P of 2. And I'm within that. Does that make sense now?
Can we push the test back to Friday?
Yeah. Okay?